Thank you. Okay, so we're going to continue with chapter 7 today. And so far we've looked at Sn2 reactions and E2 reactions, and we started with Sn1 reactions last time. So we're going to wrap that up, and then we're going to look at E1 reactions. So we'll have 4 of our reactions down, and then we're going to look at kind of how they all come together. So this is our mechanism that we looked at last time. So remember Sn1, the S is substitution, the N is nucleophilic, and then the 1 is unimolecular. So another way to think of that unimolecular part is that only one step is happening at a time. One step at a time. So in a substitution reaction, we have to lose a leaving group and have a nucleophilic attack. In an Sn2 reaction, those 2 things happen at the same time, so 2 things at a time. And in an Sn1 reaction, only 1 thing happens at a time. So we started right here with the loss of our leaving group. And then we have our nucleophilic attack. And most of the time when we do an Sn1 reaction, the solvent is the nucleophile, which means that it's usually going to be neutral. And why that matters, why I'm bringing it up, is because once we do that nucleophilic attack, we're usually going to need to also do a proton transfer. So we have this last step here to do a proton transfer because here's our nucleophile after it's been added. It's positively charged. So we just need to take off that extra hydrogen to bring the molecule as a whole back to being neutral. So if we start with a neutral nucleophile, we're going to have to take a hydrogen off of it to bring it back to being neutral after it bonds. Where we stopped last time, though, was looking at stereochemistry. So with our reactions, Sn2 and E2, we looked at stereochemistry, we looked at regiochemistry, and so that's kind of where we're at with this as well. With Sn1, so this is Sn1 specific here, when we lose that leaving group, we create a carbocation. So our substrate here has our bromine leaving group on it. And notice it has 3 R groups on it. So it just means they're carbon groups. But we have just a plain R group, one with 1 tick mark and one with 2 tick marks. That's really just a way to say there's stuff attached and they're different from each other. So it's just a really generic way to say that this is a chiral center because it has 4 different things attached to it. We don't really care what those 4 different things are. We're just saying it is a chiral center. When this reaction, or when this substrate goes through an Sn1 reaction, we will get a racemic mixture. And the reason why it's in quotes is because it's not technically racemic. What I mean by that is when we have a racemic mixture, it's 50% R, 50% S, an equal mixture. When this reaction happens, it will be nearly equal. We're going to get 2 products. One is going to have the same stereochemistry that we started with. We call this the one that has the retained stereochemistry. So this one is the same as the starting one. And then we get the one that has the inverted stereochemistry. And so this is the one that will be opposite from however we started. The one that is opposite from however we started, so the one with the inverted stereochemistry, is going to be in a little bit higher concentration. So that's why we say it's not quite racemic. So instead of being a 50-50 mixture, it might be a 55-45 mixture. So it's very close to being racemic. The reason why the one with the inverted stereochemistry has a little bit higher concentration is because of this picture on the right-hand side over here. So in this example, the bromine is our leaving group. When it breaks off, though, it's negatively charged, and it creates a carbocation. So even though there's not a bond there anymore, there's still going to be an attraction. There's still a positive and negative attraction. And so it doesn't quite leave. It's kind of slowly hangs around. And so when our nucleophile comes to form the new bond, the side where the bromine is at isn't going to be as easily accessible. That would give us the retained stereochemistry or the same stereochemistry. Instead, the nucleophile is going to be able to bond to the back side, giving the inverted stereochemistry a little bit easier. So we're going to have a little bit more of that inverted stereochemistry just because of which side is the most approachable, the side that's the easiest to get to. So stereochemistry for Sn1 is nearly racemic. Inverted stereochemistry is a little bit higher. Kind of the side note to go along with this is only going to apply if our leaving group is attached to a chiral center. If it's not a chiral center, then we don't care about the stereochemistry. If we started with something that looked like this and our bromine's right there, that bromine's not attached to a chiral center. So whether the nucleophile is on a wedge or a dash, it doesn't matter because it's not a stereocenter. Questions about the stereochemistry? Okay. We talked about the rate law for our other ones. Here's the rate law for our Sn1. Notice it only contains the substrate. So if we change the concentration of the substrate, we double the concentration, the reaction's going to go twice as fast. If we cut the concentration in half, the reaction's going to go twice as slow. If we change the concentration of the nucleophile, it has no effect on the rate of the reaction because it's not part of that rate determining step. Only that alkyl halide, only the substrate is part of the slow step. So that first step, notice how big that activation energy is for the first step. There's the activation energy for the second and the third step. Because losing that leaving group to create a carbocation is such a slow step, only the alkyl halide is going to matter in terms of that concentration rate connection. And so this is a first order reaction. Okay, E1. E1, the E is elimination, the 1 is unimolecular. So we learned Sn2 and E2 together, we're learning Sn1 and E1 together. And so E1, the 1 is telling us that only one thing is going to happen at a time. In an elimination reaction, we are always going to form an alkene. So E2s form alkenes, E1s form alkenes. So we're starting with our substrate here. There's our leaving group. And what we're going to make every single time is an alkene. We're going to do the same 2 steps that we saw with an E2 reaction. We're just going to separate them so that they're not going to happen at the same time. So we're starting with the loss of a leaving group, and we have a carbocation intermediate there. Oh, didn't mean to cross that out, meant to underline it. Let's try that again. There we go. So we have a carbocation intermediate. So that's going to tell us that first step's slow. Forming a carbocation is going to take a lot of energy because they're not very stable. They're at the top of that hill. The next step is a proton transfer. So here's our base. It's a base because it's removing a hydrogen. We know water can do a whole bunch of other things, but in this specific reaction, it's acting as a base. So the base is removing a hydrogen from the beta carbon. So remember, let me get a different color here. Where our leaving group is attached is our alpha carbon. And then anything attached to that is a beta carbon. So this technically has 3 beta carbons. They're all methyls. So really, we could do the reaction to any of those 3 and get the same thing. We'll talk about what happens if they're not all the same thing. But we're going to do a proton transfer. So the base removes a hydrogen from that beta carbon. And then the second arrow, so this one right here, we're using those electrons and we're going to form a pi bond between the alpha and the beta carbons. So we get rid of that leaving group, we get rid of that beta hydrogen, and then we form a pi bond between the alpha and the beta carbons. And then there's our alkene that we form. Regioselectivity. So remember, regioselectivity is about location. So you can kind of think of it as regions. Where is that double bond going to form? We know we're going from alpha to beta, and there's only one alpha location, but there's going to be multiple beta locations. The more stable alkene is going to be our major product. Do you remember how we rank alkene stability? How would we decide which alkene is more stable? I know
the more substitutions.
Yeah, the more substitutions. So if we have an alkene that is tetrasubstituted, that's the most stable possible, and then tri, and then di, and then mono. So we just want it to have as many substituents as possible. So more substituted. That last bullet point down here are just some of the other names that this reaction gets. Dehydrohalogenation, because we're removing a hydrogen and a halogen. Beta elimination, because we're removing something from that beta carbon as well. And 1,2 elimination, because the alpha and the beta carbons are right next to each other. So the 1 and the 2. E1 is definitely the more common, but if you're looking for other resources online, those might be some names that you use. Let's see, we talked about that. Major product is going to be our more stable alkene. This is also called the Zaitsev product. We talked about that last time. So Zaitsev is when we have the more substituted alkene. And one of the ways that we can ensure that we're making the Zaitsev product is that we're removing the hydrogen from the beta carbon that has fewer carbons. With the E2, we talked about the Zaitsev and the Hofmann, and that we could use a bulky base to have the Hofmann as our major product. We can't do that with an E1 reaction because it's happening in 2 steps. Having a bulky base isn't really going to change anything. So we can't force that Hofmann product to happen like we can with the E2. All right, we're going to do a practice one here. Let me grab my notes. So here is our reaction, and we are going to draw the E1 products. And my little hint here is that there are 3 of them. Okay, I'm going to clean off my screen. I don't know if it's going to mess up what I wrote or not. Or, add extra lines, but my screen is very dirty. Oh, much better. Okay. We're told it's E1. We're told there's 3 products. So it's given us a lot to start with. That's my alpha carbon. I know that's my alpha carbon because that's where my leaving group is attached. Those are my beta carbons. I know they're my beta carbons because they're attached to the alpha carbon. So I can form a double bond between the alpha and the beta. If you are asked just to draw the product, all you need to do is draw your carbon structure Our leaving group's going away, so we're not including that, but we need to draw a double bond between the alpha and the beta. So there's one of my products. What's another product? Where should my double bond go?
On the opposite side.
Over there?
Yeah.
Are those different structures?
No.
Yeah, those are actually the exact same structure because of the symmetry within this molecule. So that is one thing we have to keep an eye out for. If two of our beta carbons or two of the groups attached to our alpha carbon are the same, so in this case we have an ethyl on both sides, putting the double bond on either side would give us the same product. So we're going to erase this guy. So where else could I go?
Could you put the double bond on top?
Yeah, we're just going to go straight up there. Okay. So we already discovered that we can't go to all three beta carbons because two of them will give us the same product. But we do know that there's three possible products. Any thoughts on what the third product is that we're missing? It's a stereochemistry thing, not a regiochemistry thing. And it does have to stay between the alpha and beta carbon, so we can't move out to the ends.
It's with the hydrogen?
Say that again?
Wait, never mind.
Okay. So let's think about stereochemistry. For this one, could we label that as cis trans E or Z?
No.
Yeah, we can't. This one doesn't get any stereochemistry labels for two reasons, actually. So on this carbon, it has two hydrogens. So if we were to take those hydrogens and switch their locations, it wouldn't switch the label. It wouldn't switch what it is. And then on the other carbon, there's two ethyl groups. So if we were to take those two ethyl groups and switch their locations, it's the same molecule. So this one, we can't switch at all. What about the other one, though? If I put a hydrogen here, so instead of having it in this form, would we label this one as E or Z? So remember, the way we do that is we look at each vinylic carbon. So on the left-hand side, this ethyl is going to be the higher priority group. And then on the other one, the methyl would be the higher priority group. So they're on opposite sides. So this would be the E. So our third product is this isomer in its Z form. And I'm going to put that hydrogen in blue just to kind of be consistent here. So these are the same regiochemistry, meaning the double bonds in the same location, but we have the opposite stereochemistry. Questions about any of those products or where any of that came from?
Wait, why is there an E attached to the double bond on the Z?
Oh, I don't know. That should be a hydrogen. Sorry. I'm not sure where my brain was. That should be a hydrogen. Thank you. Any other questions?
So for the you determined the methyl was on the right side. Is there not a methyl on the left side too? Above the ethyl?
There is. So you mean the methyl here and the ethyl here?
Yeah.
Yeah, so I could have switched those as well. We don't want to switch both of them because we'll just be back to where we started. Is that what you mean?
So if the if the methyl was at the bottom where the hydrogen is, then that would be Z. Okay, yes, never mind, I got it. Okay, yeah, I got it.
Yeah, because we don't want to switch which carbon it's attached to.
Okay.
But if our methyl and our ethyl are attached to the same carbon, we can switch whether they're the top or the bottom. But we can't switch whether they're attached to the left or the right carbons, because then we're getting into constitutional isomers because we're moving them to a new position. Does that make sense?
Yeah, I got it.
Okay. Okay, and then in the chat, somebody asked if you would be given the hint on the test about how many products there are. For most of the questions, so I haven't actually written our test yet, but kind of in my head, and what I normally do for this kind of test is for most of the questions, you'll just be asked what the major product is. So if we look at this, let's move that to our next question then. We have 3 possible products. And if we're trying to decide which one is the major, we want to look at which one is the most stable. And so this one is tri-substituted. This one is di-substituted, and this one is also tri-substituted. So we know that the one that is di-substituted is definitely not going to be the major product because it has less substituents than the other ones. When I'm talking about substituents, we're looking at how many carbon groups are attached to the double bond. 1, 2, 3. 1, 2. 1, 2, 3. So we have 2 that are tri-substituted. Would the E or the Z be the more stable one?
Z.
So it's actually going to be the E. And our reasoning is that we want to have the biggest groups pointing away from each other. So on one of the carbons, the big group is the ethyl, and on the other carbon, the big group is the methyl. So we want those to be opposites from each other. So in this case, this one is our major product. It has the most substituents, and it has the biggest groups in the E positions or trans from one another. So most of the test questions will have you just answer what is the major product and not draw all of the possible products. All right, any other questions on this one? Okay. Sn1 and E1 are in competition with each other. And what that means is they have the same first step. We have our substrate. It goes through the loss of a leaving group, and we create a carbocation intermediate. So in this energy diagram, that first hill represents the first step of both of these reactions. And then in that second step, if we're going through an E1 pathway, we're going to get rid of the hydrogen, make a double bond. If we're going through an Sn1 pathway, we're going to do a nucleophilic attack. So here's where they're different though. They definitely have different activation energies. So notice that the Sn1 has a lower activation energy. So that means it's going to be a faster reaction. The E1 is going to be a more stable product if it has lots of substituents. So notice right here, it's shown as being higher in energy. It's shown as less stable. But if our alkene that forms is tri-substituted or tetra-substituted, then our graph would actually have it going down here. So why we're talking about this, why we care, is because if we are presented with a reaction that has something like this with some water, those are the same two reactants that we need for an Sn1 and an E1 reaction. So we have to decide, well, is it going to go through a substitution reaction or is it going to go through an elimination reaction? And here's how we make that decision. Let me get rid of this. We want to see what kind of alkene will form. And so we look at the alkene that's going to form. If the alkene is mono or di-substituted, then the major product will actually be the substitution. If our alkene is tri or tetra-substituted, then we will go through that elimination and form that alkene. So this is telling us what our major product, our major pathway will be. Now in reality, if we were to actually do this in the lab, we're going to get a mixture of products. So even though we can do this to figure out what our major product will be, we're still going to get a mixture of minor products. And that means that it's not usually the best way to do the reaction. On paper, of course, it's not messy, but in the lab, it's not the friendliest of reactions. So mono and di-substituted alkenes will be a minor product, and the Sn1 will be the major. If it's a tri or tetra-substituted alkene, then that will be that will be the major, and the Sn1 would be the minor. Questions about that? All right, there's one more thing we got to talk about with this. Well, technically a couple more things. One big thing though. Both of these have carbocation intermediates. Now, because they have carbocation intermediates, one of the things that we learned in chapter I don't remember. I'm going to make something up. I think chapter 6, actually. I was going to say 3, but I think I'm way off. We learned about all of our mechanism types. And one of the things we learned were carbocation rearrangements, hydride shifts and methyl shifts. And one of the things I said when we talked about those was that anytime you form a carbocation, you have to look for the possibility of carbocation rearrangements. And so these two reactions are showing us what's going to happen if we have these shifts. So we're starting with our substrate, we're reacting it with our base / nucleophile / solvent. Water's doing all the jobs here. And we're going to go through an Sn1 reaction for both of these. It does say plus elimination product, so really we're just kind of showing one option here. But what we're showing is how that Sn1 product will form without the rearrangement and with the rearrangement. And let me see, do I have a blank? Okay, I do. I was going to draw out the mechanism. I just wasn't sure if I had a blank slide. So we will do, let's do the first one. I don't know if we've talked about that triangle I just drew, but the reaction said water and heat. Another way to say that you have heat in a reaction is to draw a triangle. So nice quick way to do it. All right, so we're going to draw out the mechanism for this reaction, including the carbocation rearrangement. So we're going to start with the loss of a leaving group. And my angle there is a little bit weird, but I'm going to keep it the same as how it looked in my original structure. So I have a carbocation intermediate. Let's see. I'm going to draw in my hydrogen there because I need to use it in this step. So when we have a carbocation, our next step is always going to be to look at the neighbors and can we do a shift to make this carbocation more stable? Right now, we have a secondary carbocation. If I move that hydrogen over, I can turn it into a tertiary carbocation. So remember, rearrangements only happen if they improve the stability of the carbocation. So here's how we do the shift. I'm going to start my arrow at the electrons, and I'm going to go right to that carbon. So this is my, this is my hydride shift, would be the specific name of it. We could also just call it a carbocation rearrangement. So now my carbocation is over there, and we have a tertiary carbocation. Now, what happens in this reaction, though, is that we're going to still form both products. So I'm going to redraw this one, and this is without the rearrangement, because we're going to get both. Even though that tertiary carbocation is more stable, the nucleophile can react with the original carbocation faster. So we kind of have a mixture here of what's the most stable versus what's the fastest. So now we're going to do, and I'm just going to kind of do these in tandem next to each other here, but we're going to do a nucleophilic attack. So my nucleophile is my water. So I'm going to go from the electrons on my oxygen to that carbon for both of these. Oh, let's label these nucleophilic attack. Now you don't have to draw in that hydrogen that we moved over, the one that got transferred. I'm drawing it in because we moved it over. So it became part of the reaction. We used a neutral nucleophile. We started with water. And so that means that once it bonds, it's now positively charged. So I'm going to draw in one more water molecule so that we can do a proton transfer. So we want to go from that oxygen to that hydrogen and break that bond. So this is a proton transfer. And so those are our two products that we get. This is our product without any rearrangement. And this is our product down here with the rearrangement. The major product will always be the one with the rearrangement. It's creating a more stable carbocation. And so because of that, it will be our major product. Questions about any of those mechanism steps?
Can you just show your process, because it's kind of like all over the place for me, and I didn't follow it as quickly.
You mean just like the pathway I went?
Yeah.
So there's two pathways on here. They both start right here, doing that loss of a leaving group. And then one pathway goes up this way. And then the other pathway goes down this way. So this one going over into going to the right and up is without the carbocation rearrangement. And then the one going to the right and down is with the carbocation rearrangement.
Okay.
And so really, let me erase that green arrow, make this a little bit more accurate. We should just go from there to there. So a question in the chat asks how to explain how the carbocation is secondary on the bottom. So remember, the way we decide if it's primary, secondary, tertiary is just how many carbons it's attached to. So there's our carbocation. It's bonded to 2 carbons. And so that's what makes it secondary. And then there's our carbocation, 1, 2, 3. It's bonded to 3 carbons. That's what makes it tertiary. So we're just counting how many carbons it's bonded to. Anything else on that one? Okay. All right, there's a lot on this slide that is kind of beyond what we need to know. So we're going to kind of narrow it down. But this is talking about solvent. And when we talked about E2 and Sn2, we went through everything. We did substrate and nucleophile and base and solvent and all the stuff. And so we're doing the same thing here. But really, that's the takeaway from this slide. When we do an Sn1 and E1 reaction, let me rephrase it. When we do an Sn1 or E1 reaction, we want to use a polar protic solvent. And so a few slides back, we looked at the difference between polar protic, polar aprotic, and nonpolar solvents. But polar protic means that it's polar, and the protic part means that it can hydrogen bond. So water definitely falls into this category. Different alcohol groups fall into this category. And those are going to be the ones that we see most common. This slide is showing us how fast the reactions are happening in polar protic versus aprotic. The dielectric constant is a measure of polarity. It is something to ignore. Really, the takeaway from this is we want to have a solvent that is polar protic. The reason for that is that it can help stabilize that carbocation. One of the differences between the protic and the aprotic is whether or not it can help stabilize an anion. And our protic solvents can do that. That means that once that leaving group breaks off, that protic solvent can surround it. And the reason why we want that to happen is because we want our carbocation to stay a carbocation. We don't want that leaving group to come back and bond with our carbocation again. Notice that it's a reversible reaction. That carbocation is super reactive, but we don't want the leaving group to react with it. We've already done that. We're trying to get rid of the leaving group. We want our nucleophile to come in and react. So the solvent can kind of surround that leaving group, keep it occupied, while something else new can come in and react with our carbocation. So that solvent's going to help stabilize the carbocation and keep the leaving group busy. So really, the whole purpose of this slide is that first circle. If you're making a reaction chart, if you're making a reaction notebook, or even just like reaction summary pages, polar protic solvents, so waters and alcohols. Last slide for this section is when we have a better leaving group, we're going to have a faster reaction. So because that first step is our rate determining step, which is really just the leaving group leaving, we want to have the best leaving group possible. And so this is telling us that iodine is the fastest, and then fluorine is the least fastest. And if you look at the periodic table, this is a measure of size. So iodine is the largest in size, and fluorine is the smallest in size. And so this is whether or not they're going to be stable on their own, or how stable they're going to be on their own. Another measure of the substrate and how reactive it's going to be is the carbocation. The more stable the carbocation is that will form, the faster the reaction, the better the reaction will be. So with E2 and Sn2, we talked about what type of substrate we had. With Sn1 and E1, it's going to be essentially the same. Primary and secondary carbocations just aren't going to happen. They're not stable enough. Tertiary, so 3 carbons attached to our carbocation, benzylic and allylic are all going to be stable enough carbocations that this reaction can form. So if we tried to do a reaction like this, we tried to do an Sn1 reaction like this, the answer would be no reaction, because if we lose that leaving group, we would form a primary carbocation. That's not going to happen. No primary and no secondary. They're just not stable enough. But tertiary, benzylic, and allylic. Now notice that benzylic and that allylic, these are both primary benzylic and primary allylic though. So because they have that extra stability from resonance, because of that neighboring double bond or multiple double bonds, that adds in that extra stability. So benzylic and allylic, whether they're primary, secondary, or tertiary, are all good to go. Oh, wait, let me go back. Notice just the sections here. We're going from 7.9 to 7.11. So we are skipping 7.10. So it won't be on the test. We're not talking about it. All right, this takes us to I want to say our last section. It's not our last section. I think it's our last big section. There's a couple smaller ones after this. What this section is looking at is, what does all this mean? What do we do now? We have 4 possible reactions for an alkyl halide. We have a carbon with a halogen bonded to it. We're reacting it with something that's a little bit negative. What's it going to do? Is it going to go through an Sn1, Sn2, E1, or E2 pathway? So what we're going to look at in this section is, how do we decide which reaction is actually going to occur? And unfortunately, there's not always one right answer. Oftentimes we'll have a mixture of answers or a mixture of products. And so we use kind of a flow chart or a decision-making process to help narrow it down and help us get to the major product or the best possible answer. And this is really our little pathway here of how we're going to make that decision. We start by looking at our reagents. Are we using a nucleophile or are we using a base? Because remember, substitution reactions use nucleophiles. Elimination reactions use base. So that should hopefully cut our options down from 4 to 2. Not always, but hopefully. Next, we look at our substrate. Is our alpha carbon, so where our halogen is attached, primary, secondary, tertiary, benzylic, allylic? Because that can help us decide, will it form a stable carbocation or not? Will it form a highly substituted alkene or not? It's going to, again, help us decide which pathway to go down. Once we know which pathway we're going down, Sn1, Sn2, E1, or E2, then we can decide regio and stereochemistry. where will that double bond form? Will the nucleophile have the same stereochemistry or the opposite stereochemistry from where we started? So that's getting into the details of our product. All right. First step, the reagent. So the reagent is usually what's drawn above the arrow. Not always. It's not a rule that it has to be drawn there, but usually it's drawn above the arrow. And for these reactions, we are deciding, are we using a nucleophile or are we using a base? For substitution reactions, we use nucleophiles. For elimination reactions, we use bases. Now notice even within those, we're dividing them out. So for the 2s, Sn2 and E2, we want to use something that's strong. So an Sn2 reaction uses a strong nucleophile, and an E2 reaction uses a strong base. And then for the 1 reactions, we want to use something that's weak. So Sn1 uses a weak nucleophile, and an E1 uses a weak base. Reasons for this. When we're doing a 2 reaction, Sn2 or E2, everything happens at the same time. So we want to use something that's strong so that it reacts with our substrate immediately. With Sn1 and E1, we want to create that carbocation first and then have our nucleophile or base react. So we want it to actually be less reactive. That's why we want to use something that's weak. So this table is from your book. I think I added the red labels on the top here. But this table is from your book. It is definitely not an all-inclusive table, but it's a good resource and a good representation of some of the reagents you will see. And so it's divided into things that are strong bases but weak nucleophiles, strong bases and also strong nucleophiles, weak bases but strong nucleophiles, and weak base, weak nucleophile. So we have alcohols and waters. We have halogens and sulfurs. So if we could just sum this table up, halogen and sulfur. This is negatively charged oxygens. Over on the far right, those are neutral oxygens. And then the first category on the left, those are the weird ones. So we have NaH, so that's just a negatively charged hydrogen. And then we have DBN and DBU. So look over here. That's what they look like. They're nitrogen containing organic molecules, so they are organic bases. We use that term because they're carbon based. The nitrogen is what makes, I shouldn't use the word base in 2 different versions in the same sentence. Let me try that again. These are carbon containing molecules that have a nitrogen in them. The nitrogen is what allows them to act as a base in a reaction. They get abbreviations DBN and DBU because their names are super long and kind of weird because they are bicyclics. You won't ever see their names fully written out except for right now. But yeah, these definitely aren't the only things that we will see, but it's a good way to help us categorize stuff. All right, so there's our first step. We want to decide what type of reagent we have. Our second step is to look at our substrate. So this is a super helpful table, but right now we're just looking at this left-hand column. It's divided into primary, secondary, and tertiary. So we're looking at our substrate, and we're looking at that alpha carbon. So the one that I drew right now is secondary because that alpha carbon is bonded to 2 other carbons. That alpha carbon is tertiary because it's bonded to 3 other carbons. And so we can categorize what type of carbon we have, what type of alpha carbon we have. And then notice the top up here. This is the same as that slide, our previous slide, these are the reagents. So if we have a strong base that is a weak nucleophile, no matter what type of substrate we have, it's going to go through an E2 reaction. If we have a weak base that can also act as a strong nucleophile, it will go through an Sn1 reaction only if we have a good carbocation, so meaning a tertiary carbocation, and it will go through an Sn2 reaction if the carbocation isn't stable, so a primary or a secondary carbocation. Now there's a couple spots. I'm going to erase all of those circles. There's a couple spots where we have some shared boxes. So that's what I want to talk about. Let's see. What color will show? Okay, make sure my color shows up there. So specifically the E2 and the Sn2 boxes. When we have a primary, so if we're looking at this box right here, when we have a primary alpha carbon, because it has low steric hindrance, our Sn2 will be our major product. So that's what this means. Because the Sn2 is taking up more of the box, that means that the Sn2 would be the major and the E2 would be the minor. We can force this E2 to be the major if we use a bulky base. So something like tert butoxide. Let's see. Ooh. So something like that. In the box underneath it, the E2 is our major. Sn2 is the minor. One thing you'll also see with elimination a lot of times is you'll see heat. The heat helps the reaction form if it's elimination. Hey, little kitty cat. My goodness, she's so tiny and so loud. All right, in the last category, well, actually, let's talk about the third one here. So in this category, I already said that the Sn1 will form if we're doing tertiary, and really it's forming because we're going to have a stable carbocation. So notice that benzylic and allylic aren't on this chart, but they would fall into this category because they are stable carbocations if we have the appropriate reagent, meaning weak base with a strong nucleophile, a weak base. Okay, let's start that sentence over. Something that could be categorized as a weak base or a strong nucleophile, then it would go through an Sn1 reaction with that benzylic, allylic, or tertiary substrate. All right, last category. If we have a weak base or a weak nucleophile, it's going to go through an Sn1 or E1 reaction. But again, we have to have a stable carbocation. So it's down here in the tertiary category. But I'm let's see, I'm trying to decide how to do this and not make it too messy. I think I just have to make it a little bit messy. We'll just put stars here. We're just going to say benzylic or allylic would also fall into these categories as well. Now, in that last box, Sn1 and E1 look like they're sharing that box equally. But what we just talked about a couple slides ago is that this will be our major if we can make a tri or tetrasubstituted alkene. And then our Sn1 will be the major if the alkene is mono or disubstituted. Actually, we'll just leave it at that. This is a super helpful chart. This chart will help you get through practice problems. Definitely do practice problems without this chart as well, though. Don't fully depend on it. Another thing that can be very useful instead of using this chart is to kind of create some type of chart or decision tree yourself. You can always get ideas if you Google, so Sn1, Sn2, E1, E2 decision tree, or reaction diagram, and just look at Google Images and look at how other books, other professors, other students have kind of created these. Making something yourself is definitely going to help it stick in your head better than trying to memorize or learn somebody else's. Now, I do want to give you a bit of warning. I am teaching this to you the way that our author has laid it out. And I word it that way because our author actually kind of simplifies this a little bit. So if you look at other resources, YouTube, Khan Academy, other websites, whatever, you might see some things that we haven't talked about, or some things that are a little bit more complex than what we've talked about. It doesn't mean that that's wrong or what we've done is wrong. It just means that there is more to this than what we've talked about. And so just be a little bit hesitant on other resources for this, because it already is a pretty heavy topic, and I don't want that extra information to make it more difficult for you. So just a little caution there. All right, last decision then. We've gone through our reagent, we've gone through our substrate, we've decided it's going to go through an E2 pathway. We've decided it's going to go through an Sn1 pathway. We've figured it out. The last step is regio and stereo. So the regio decision is, where's the reaction going to take place? So for the substitution reaction, that's easy. The nucleophile is going to bond to the alpha position. For an Sn1, if the carbocation can go through a rearrangement, then our major product will be from the carbocation rearrangement. So it will generally bond where the leaving group was attached, unless a carbocation rearrangement takes place. For an elimination reaction, we've talked about the Zaitsev and the Hofmann product. So for an E1, the Zaitsev is always the major product. For an E2, the Hofmann product will be the major if we're using a bulky base. And the Zaitsev will be the major product if we're using a small base. The other half of this table, and this table is from your book, by the way. The other half of this table is the stereochemistry side. Sn2, we get the inversion. Sn1, racemic, nearly racemic, kind of racemic. E2 and E1, trans. Now, this isn't a true definition of the word trans. When we're saying trans here, we're talking about the two big groups. So the big group on each vicinal carbon should be trans from one another or opposite from one another. There's this whole extra little paragraph up here about the anti-periplanar side of E2. We did talk about that last time. It gets pretty specific, but it only happens when there is only one beta hydrogen. So it's a very specific set of scenarios. All right, with all of this, we're going to practice. So I have these two on to one slide because normally we would do this on the whiteboard and I would have this available for us to look at. So we might just need to come back to this. but let me draw out some practice problems. We're going to go through some reasoning here. So what we're going to do for each of these is we're going to decide what pathway it's going to take, and then we're going to draw out what the major product is. And so this is how you will see this on the test. I mean, literally, I'll just have a box over here and probably a little line underneath it. On that little line, you're going to put Sn1, Sn2, E1 or E2, and in the box, you'll draw in what the major product is. I'm going to get rid of these for now just to make it less cluttered, though. All right, so we've gone through nearly a chapter of this information. How do we actually utilize it? So I'm going to go back to the previous slide, the one that has the tables on it, so we can use that information. But before we go back to that tables, we just need to kind of gather information on our first reaction. There's my alpha carbon. What type of carbon is that? Primary, secondary, tertiary, benzylic, allylic?
Primary.
It is primary. So we have a primary substrate. We have a negatively charged oxygen. Okay. So negatively charged oxygen, that means we have a strong base. Well, let me rephrase that. We have something that can act as a strong base or a strong nucleophile. So we know that we're in this section. We know that we have a primary substrate. So we're in that section. So that puts us right here. So that tells me that my Sn2 pathway will be the major pathway. We know that there's an exception to that. If we're using a bulky base, then the E2 will be the major pathway. But we have hydroxide. Hydroxide is not bulky. It's very small. So there's my answer, part of my answer. I know that it's going to go through an Sn2 pathway. So there's my first step. I'm just going to put Sn2 on the side over here. Now for this to go through an Sn2 pathway, I know that it has to lose the leaving group and my nucleophile is going to bond to it. So there's my carbon structure without the leaving group. There's my nucleophile. The regiochemistry for this is just that the nucleophile bonds to where the leaving group was. The stereochemistry with Sn2 is that it's going to be inverted. But I don't need to worry about stereochemistry for this specific example. Do you know why? Do you see why? So my alpha carbon to start with isn't a stereocenter. It's not a chiral center. So because of that, we don't need to worry about the stereochemistry we're ending with. There's two hydrogens right here. So whether we drew that alcohol with a dash or a wedge isn't going to make any difference at all because it's not a chiral center. So we only need to worry about the stereochemistry for our substitution reactions if we're starting with a chiral center, if we're ending with a chiral center, but neither one of those are happening here. Questions about this first reaction? Okay, let's look at the second one then. There we go. There's my alpha carbon. What type of carbon do we have this time?
Tertiary.
Good. And we have one of our neutral oxygens. We have an alcohol. So neutral oxygen, tertiary carbons. We're going to go back to those tables. I think I probably need to erase all kinds of stuff here. There we go. Let's do that. What did we have? Methanol? We had methanol. Okay. So we have methanol. Even if you didn't recognize that CH3OH is the same thing as MEOH, that doesn't really matter. We know it falls into the alcohol category. We know it's going to fall into the category with the neutral oxygens. So all of those are in that first box on the right. So our alcohol can act as a weak base or a weak nucleophile. We have a tertiary carbon, so that means that we're down here. So whether our Sn1 or our E1 pathway is the major pathway, we have to look at what type of alkene can form. And so this will be the major if we can make a tri or tetrasubstituted alkene, and the Sn1 pathway will form if the alkene is less stable. So let me show you what I mean by that. So we're going to look at what our possibilities are. There's my carbon group without the leaving group. I could put a double bond right there. I could put a double bond right there. I could also put a double bond on the other side, but it would actually be the exact same as what we started with. So these are my two different E1 pathway possibilities. I've made a double bond between the alpha and the beta carbons in both possible locations. My Sn1, there's my methyl, there's my OCH3. So the hydrogen on that oxygen gets removed during the reaction. We're not showing the mechanism. It's not asked for these reactions, but that would be my product there. So we haven't fully answered the question though. Which one of these is going to be the major product? Do you think it's going to go through the E1 pathway or the Sn1 pathway?
E1.
It is going to go through the E1. And that guy right there is going to be our major product because it's a tri-substituted alkene. The other ones, that one and that one, those would both be minor products. So technically for this reaction or this problem, we wouldn't have to draw those because it's only asking for the major. Sometimes you have to draw them to like figure out what's happening, but they wouldn't be necessary for your answer for this. Yes, so in the chat, somebody asked if I can show how it's tri-substituted. So we're looking at the double bond. Here are my vicinal carbons, the carbons that are part of that double bond. We're just counting how many carbons are attached to it. 1, 2, 3. That's what makes it tri-substituted. This one, there's my vicinal carbons, 1, 2. That one is di-substituted. And so if we can make tri or tetra, that will be our major product. If that tri-substituted one wasn't an option, then our Sn1 would be the major product. So if we were to rank these, this one would be in first place, this one would be in second place, and then that one would be in third. Okay, so the question in the chat, I'm not sure if I understand it. I think I need to read it out loud. If Sn1 prefers primary, can we assume elimination or do we have to weigh the options? So Sn1 does not prefer primary because with Sn1 and E1, it's going to form that carbocation. So Sn1 and E1 don't like primary or secondary. So I'm not sure if that answers your question, if that helps at all. But in terms of like weighing the options to decide if you're going to have Sn1 or E1, I would definitely draw out what your possible alkenes would look like to decide how many substituents it has. That's going to help you make that decision. Is this the slide you're asking about in your question? No. Sorry, this one. I think I went too fast. We ranked the substituents. Rank the substrates. So in ranking the substrates, though, I'm going to go back to this slide. So notice that Sn1 and E1 are only happening in that tertiary section. So if we have primary and secondary, Sn1 and E1 won't happen. So if we had something like this, and we had a weak base, oh, no. We had something that was a weak base, weak nucleophile, like water, the answer would be no reaction, because this would fall into this top category. It's primary with a weak base, weak nucleophile, so it's just not going to go through any of our reactions. All right, I think we have one. There we go. One more example on here. So what type of substrate do we have? Primary, secondary, tertiary?
Secondary.
Secondary. We have NaH. That sodium we don't really care about. This is a negatively charged hydrogen. So it's a hydride. So it falls into the category that I just said was kind of the weird category. It's the ones that just, there's not really a trend between them. Sorry, wrong direction. There we go. Let me do a little erasing so we're not looking at the other problem. So we have sodium hydride, which is a strong base or a weak nucleophile. So regardless, it's going to be E2. We're right here, we're secondary, but with that category, strong base, weak nucleophile, it will always go through that E2 reaction. So E2 tells me that it's going to be an elimination reaction. So we have two different beta carbons. Beta, beta. But if we're only drawing the major product, should I go to the beta on the left or the beta on the right? Which one would give me the more stable alkene?
The right.
Left.
I just like that you guys said at the same time, but opposites. So it is going to be the right. And the reason for this, I'm going to draw out both and we'll talk about why one's better than the other. There's the one going to the right. There's the one going to the left. And then technically there's one more. That's going to the right also, but it's the cis. So we have the one going to the right trans, the one going to the right cis, and then the one going to the left. And our major product is going to be this one. And here's how we decide that. This is di-substituted. This is di-substituted. This guy's only mono-substituted. This one's di and trans, and this one is di and cis. So having more substituents, so di is more than mono, and then having trans versus cis puts this one into our major category. So we want to have as many substituents as possible, and we want to have the biggest group. So in this case, they're not big, but the big group on each side are methyls. We want to have those pointing away from each other for sterics. So the di-trans would be our major product. The di-cis would come in second place, and then that mono would be in third place. Questions about any of those? Okay. I could have spread those out a little further. I forgot I had a second slide there. So we have a couple of reactions left in this chapter, and they are looking at alcohols for the most part. When we have an alcohol attached to our carbon group, it's not a good leaving group. So we've talked about leaving groups as halogens, mostly chlorines and bromines. That's what we look at most of the time. But we can do these reactions if our leaving group is an alcohol as well. But we have to turn the alcohol into a better leaving group first. And so what we use are these. So we turn our alcohol into a mesylate, a tosylate, or a triflate. So really this group right here, here, and here is replacing the hydrogen. So we have our carbon chain, we have our oxygen. We're taking that hydrogen off and replacing it with this other group. And the entire purpose is because this other group is a better leaving group. Here's our reaction to do this. So we're starting with our alcohol. We're reacting it with tosyl chloride. So this could also be methyl chloride or trifle chloride. So it's really that group we're attaching, and then just a halogen just to make it neutral. PY is pyridine. I'm not sure if we've talked about pyridine yet. Pyridine's a pretty common solvent. It's definitely one that we will see pop up every now and then. But it can also act as a base. And so that's one of the reasons we use it, because as a solvent, it can also remove hydrogens. So I'll draw out what it looks like for you. So it kind of looks like a benzene ring, but one of the carbons has been replaced with a nitrogen. Really just for your own knowledge, not a big deal. So in this reaction down at the bottom, then, this is essentially like a pre-reaction. So if we want to go through Sn1, Sn2, E1, or E2, and our leaving group is an alcohol, we would do this reaction first, and then we could go through any of those other pathways. And then we have a couple other things that alcohol can do. This slide's going to look busy, but it's because I wanted to fit everything in one spot because they're very related to each other. This is also a way for us to react alcohols. So notice that in each of these, we're starting with an alcohol. In the first one, we have a primary alcohol, and it's going through an Sn2 pathway. And so let's see. I think I have it written up here. I'll draw a little arrow here. So if we're starting with a primary alcohol, it can go through an Sn2 or E2 pathway. We have to make it into that good leaving group first, though. And so we can do that with the tosylate, triflate, mesylate groups. We can also do it by adding HX, so a hydrogen with a halogen. This turns our alcohol into a water molecule, which makes it a much better leaving group. If we're starting with a secondary or tertiary, then our alcohol can go through an Sn1 or Sn1 or E1 pathway. So kind of the same thing. We can use that HX group because then it will turn it into a water molecule. Here we're just using hydronium. In all three of these, even though they look different, the purpose of all of them is to add a hydrogen to that alcohol group to turn it into a water. So we want our OH to become OH2 because that makes it into a better leaving group. All right, this slide looks scary, I know. What this slide is showing us, though, is essentially a summary of this chapter. At the ends of pretty much every chapter we look at, there's a reaction summary. This one is a little bit more generic than a lot of the ones we look at because we've talked about reacting things with nucleophiles. Nucleophiles can be a whole bunch of things. So here we're starting with an alkyl halide, and those are some examples of nucleophiles that we can use. So by starting with an alkyl halide, we can make a nitrile, an ester, a thiol, an ether. Those are the substitution sides. So Sn1, Sn2. If we react it with a base, we can, not that one. We can make an alkene. So that's the elimination side. Over here, we have some of the alcohol stuff we just looked at. And then down here is the same. So turning that alcohol into a good leaving group that can then let us do substitutions or eliminations. So this is kind of a busy, kind of an overwhelming pathway map, but having these reaction maps can be really useful. One way to help learn and utilize the reactions in the chapters that we talk about is picking a functional group that we've started with. So in this case, alkyl halides, and then trying to turn it into something else, trying to make an ether, trying to make a carboxylic acid, trying to make a ketone, and seeing if you can create that pathway. Do I have one more? No, I don't have one more slide. When we get to the end of chapter 8, we're going to do something called a multi-step synthesis. And that's where we link together multiple reactions to make something bigger. Chapter 8 is all about alkene reactions. So we know how to turn an alkyl halide into an alkene. And then in chapter 8, we're going to learn how to turn that alkene into other things. So we'll be able to kind of group reactions together to start with something smaller or with a specific functional group and make something larger that has different functional groups. So we'll kind of revisit this slide and utilize those reactions as a whole as we're wrapping up chapter 8 or as we're looking at chapter 8 stuff. So don't let this slide overwhelm you because we've talked about all this already. Nothing on here is new. It's really just the chapter summarized into one slide. So as you're doing practice problems, utilize this. This is probably the most important slide in the whole chapter. It's going to help get you through pretty much all of your practice problems. Remember, though, that it's not all inclusive. So as you're looking at stuff and you have a reagent that's not on this list, think about how it's related to the ones that are on here to figure out what category it would fall into. The other thing to keep in mind is that this only has primary, secondary, and tertiary. So we don't have benzylic or allylic on here. So you have to determine how those will fit in based on whether or not we form that carbocation. So it's a good overview, but not all encompassing. Okay. I think I'm done. I think we're done with time too. Oh, we are. Perfect timing. All right. That is it for lecture. That is it for chapter 7. On Wednesday, we will start chapter 8. Today, we do have an experiment though. So go click on the other link, take a couple minute break, and then we will talk about today's experiment. And it's a Beyond Labs one. So the pre-lab part will be pretty quick, unless we have Beyond Labs questions, which is completely okay. But I will see you in a few minutes. I will hang out here if you have any questions for me.
Thank you.
Thank you, guys.
Are we